Now I explain the concept of covariance function. Covariance function is a mathematical model which gives us the covariance between two anomalous quantities at the surface of a sphere. Consider two spheres. One of them, we have meridians, which are converging at the pole. And now consider a point a point at the surface of this sphere. Let me call this point A. The geocentric distance, a geocentric angle from the pole and the point A is known as colatitude, and we show it with theta. And also, if we consider one meridian as a reference and one meridian passing through A, the angle between them is known as longitude. It means that the point A can be found at the surface of a sphere by these two angles. Now, consider that we have 2 points at the surface of the sphere. On the right side, you see point A and point B. Let me draw this B a little bit closer. Point B here. And we assume that point A is a pole. And if it is a pole, there will be many meridians passing through this pole, or the gray circles, and one of them passes through the point B as well. The geocentric distance from A and B in this case, I call it psi, or geocentric angle. Geocentric angle between point A and B is psi. And also, the angle, which is like a rotation around this pole, is called azimuth or alpha. Alpha is very similar to lambda, and psi is very similar to colatitude. For example, I can write on the left-hand side spherical harmonic expansion of gravity anomaly, just as an example. Based on the spherical harmonics with arguments theta or lambda, colatitude and longitude. In the other case, on the right side, when A is a pole, I can write a very similar spherical harmonic expansion. Delta G and M. Y and M. And this time psi and alpha. Consider that for the first case, the colatitude are considered from pole, and in the right hand side, the point is the pole is actually the point A, 1 point. Now let me define the covariance between two quantities by spherical harmonics. If a point A is pole, the covariance, I write here psi, not alpha, but I will explain why. It will be summation over n, summation over m, c and m, y and m, psi and alpha. In order to show or explain why alpha is missing on the left hand side, let me expand the spherical harmonic function. I rewrite this expansion again, based on sine and cosine spherical harmonics. So CNM cosine m lambda sine and is sine m lambda and p and m cosine. But here instead of colatitude I write psi. If I do that, therefore all this lambda in this equation should change to alpha. Yes. And we want to assume that, or we have to assume that the gravity field is isotropic. It means that it shouldn't be dependent on the azimuth alpha. It is possible only for the case that m is equal to 0. So if in that case m is equal to 0, this mathematical model will not be a function of alpha or the azimuth. And in that case, it will be simplified to summation over n, Cn, Pn cosine psi. This is why the reason that I didn't write covariance psi and alpha, because always we assume that the covariance function is isotropic. Otherwise, the mathematical model will be complicated. Now, I explain if this covariance function is like that, and we have covariance function on the vertical angle and the spherical angle from point A to B, it will be clear that by increasing the distance from the point A, which plays the role of pole, the covariance reduces. It means that the points that which are closer to R, to point A, they have more correlation. They are more correlated to point A than the points which are far from point A. And it is quite rational. Now the point is that if it is the mathematical model of the covariance function, what will be the Cn, or the spectrum or a spectra of this covariance function? So I write the covariance function is equal to summation Cn Pn cosine psi. Now the goal is to derive Cn. But this mathematical model actually is very similar to the formula of the legend or Laplace expansion of covariance function. It is Laplace expansion of covariance function. So if it is Laplace expansion, the Laplace coefficient will be 2n plus 1 over 4 pi integration over the unit sphere, the covariance function, Pn cosinus psi, and this. Note that since one point here is considered as pole, therefore this psi is not actually a distance between 2 points, but 1 point is actually 4. Then it's no problem. So therefore, I can write also covariance function as the average of the square of, in that case, gravity anomaly, but we can consider for any anomalous quantity. So now I put back actually this covariance function to the equation of Laplace coefficient. And since I want the covariance, I consider one point delta G and other one delta G prime. It means that they are not at the same point. If they are at the same point, it would be variance. I want the covariance between two anomalous quantities. So, as we see here, delta G prime, Pn cosine, the sigma integral n2n plus 1 4 pi represents actually the Laplace coefficients of delta G. Therefore, I will write the equation again, 1 over 4 pi summation integral over sphere delta G n, the sigma. So it is an averaging operator, as you see here. Global average, delta Gn is a full spectrum. Actually, all frequencies are there with one frequency from delta G. So then I write the spectra of the gravity anomaly for the first gravity anomaly, the formula, and then delta G n, the sigma. It should be m prime so that the degrees are not mixed. Now I rewrite this equation. It means that we know that these Laplace coefficients are actually spherical harmonics. If I expand them in spherical harmonics, as I have shown already, and apply this integral and 1 over 4 pi, I will come to orthogonality, a formula for the orthogonality of the spherical harmonics. Then it will be much simplified to the Free-Morse equation that we have for degree variance. We will see that. So I will put this here based on spherical harmonics, and for the other one, summation over m delta G n and y. And again, as I explained, 1 over 4 pi and 2 spherical harmonics, as you see here, which is actually the orthogonality we can use the orthogonality properties of this harmonics, as I already shown in the previous video. Then these two summations will be simplified to one summation, which is delta G mn squared, which is in fact degree variance. Therefore, the covariance function, a spectrum or a spectra, is simply the degree variance of the anomalous quantity.